Okay, in this video, we are going to look at the conversion of an epsilon-NFA to an NFA. So we have already discussed the idea of epsilon closure in one of our previous videos. And the understanding of the epsilon closure of a epsilon closure is very important while we try to convert epsilon-NFA to NFA. Now, before moving into the conversion, let's look at some of the facts on epsilon closure. So the epsilon closure is never an empty set. We have already encountered this. For example, from this diagram, if you look at the epsilon closure for Q0, Q0 itself is going to be a member of the epsilon closure of Q0. So since here there are no epsilon transitions out from Q0, the epsilon closure of Q0 just contains Q0 itself. So let me write it to make it clear. So the epsilon closure, I'm writing epsilon close for closure. Okay, epsilon closure of Q0 is going to be Q0. So at least that state will be present in that closure. Similarly, epsilon closure of so if you look at the epsilon closure of Q1, so that's also going to be Q1. Okay, but look at the epsilon closure of Q2. So if you look at the epsilon closure of Q2, then you can see that Q2 itself is a member, and you can see that there is a transition, epsilon transition here going to Q0. So Q0 also becomes a part of the epsilon closure of Q2. So this fact is very relevant. Epsilon closure is never going to be an empty set. And another one is that epsilon closure for a null set is going to be a null set, right? So these are some two facts which we may encounter while we are applying the conversions. Okay, so now our task is to convert an epsilon-NFA. Our task is to convert an epsilon-NFA to an NFA, right? Now, what is the difference between epsilon-NFA and NFA? Epsilon-NFA contains epsilon transitions, right? But an NFA does not contain any epsilon transition. So if you are successful in removing all the epsilon transitions from an epsilon-NFA, then we will get an NFA. So what we are going to essentially do is that we are going to remove all the epsilon transitions from the epsilon-NFA. Okay, in some logical way, and then we will get its equivalent NFA. And remember, once you are getting the NFA, you can also convert it to a DFA, right? So if you're asked to convert an epsilon-NFA to a DFA, you can actually convert it first to okay, so let me take my pointer and explain. So if you're asked to convert an epsilon-NFA to a DFA, what you can do is you can convert epsilon-NFA to an NFA, okay, and then you can convert an NFA. You already know how to convert an NFA to its equivalent DFA. So that means you can apply that two-step processes. You can convert epsilon-NFA to NFA and then an NFA to DFA. That's possible, right? You may be also asked about converting an epsilon-NFA to an NFA itself. So in that case, you have to remove all the epsilon transitions logically and then creates its equivalent NFA, right? And remember, there is a method for directly converting an epsilon-NFA to the DFA itself. Okay, so we may not apply the two-step process, right? That is, you are converting an epsilon-NFA to NFA and then an NFA to DFA. Instead of doing that, we can also convert directly an epsilon-NFA directly to a DFA. So we'll look at a couple of examples for all this. So now let us look at how can we convert an epsilon-NFA to an NFA with a very simple example. And it's also a very typical example. So there is a mathematical way of doing this in a very guaranteed manner. So using some formulas. So, but before actually looking at the mathematical approach, let's look at the commonsensical approach and approach of how we are doing this stuff. Okay, so if you look at the direct commonsensical approach, then the mathematical approach will make more sense to you. Okay, so what we are interested in is to convert this epsilon NFA to NFA. So we know that the NFA contains, looking at the alphabet set, the alphabet set contains 0 and 1, right? And we are only interested in the transitions on 0 and 1. So we are not going to define epsilon transitions for an NFA, right? So I've already made a table here representing all the states given in the epsilon NFA, which are A, B, and C, right? And now I'm going to define the transitions of 0 and 1, right? So this is going to be interesting. So when I say zero, okay. So when I say zero, a zero can be, zero can be 0. Epsilon is also 0. 0 epsilon is also a 0, right? So in general, 0 and combined with any number of epsilons is nothing but 0. So all these things we treat it as 0. Right. Similarly, the epsilon symbol can occur in the left side also. For example, the epsilon 0 is regarded as 0. Epsilon 0 is regarded as 0. Any number of epsilons in front of 0 is also regarded as 0. Okay, so all these things that you see here is nothing but a 0, right? So what we are essentially going to do here is that we are going to look at all possible transitions by putting epsilon before and after in multiple combinations, and then we are going to look at the states I can reach from the given state. Okay, so for finding the resultant states on 0 transition. Similarly, we can do for the transition on 1 as well. Okay, so for 1, we are going to look at not just 1. We are going to look at 1 followed by any number of epsilons, and epsilons followed by any number of 1s. Any number of epsilons followed by 1, right? So that's the general commonsensical approach. So let's now look at this diagram and try to understand this. So if you look at A and the transition on 0, we are going to define the transition on 0. Now the transition of 0 upon A. Okay, so we have to write the transition of A upon 0 here, right? So A on 0 directly gives A. That's there. And here, look at here. See what happens if I'm putting 0 epsilon. Okay, so all epsilon moves are perfectly valid with 0. So 0 epsilon gets me to B. So B is also a valid state here. Again, look at here. 0 epsilon gets me to C, right? So it means that transition of A, transition on 0 upon A, I can actually reach anywhere. I can reach to A itself. I can reach to B. I can also reach to C by using the epsilon transitions. Okay, so look at here. 0 epsilon gets me to B. 0 epsilon gets me to C. Okay, so all these states are possible upon 0 transition. So let me write that here. So it means that I can actually go to A, B, and C upon 0 transition, right? Now what I'm now interested in is looking at the transition of state A on 1, right? So if you look at A on 1, there's no direct transition of A on 1 defined here. But look at here, epsilon 1 is also 1. So epsilon 1 gets me to B. Okay, so I can write B there. So again, epsilon 1 gets me to C as well. Okay, so it means that essentially, if you get a 1, it equivalently means epsilon 1 or epsilon 1, So it means that I can reach to B and C. I can reach to B and C if I'm getting a 1 on A. From state A, if I'm getting a transition, if I have to look at the transitions on 1, then I will get B and C. The very same way, we can also look at the transitions on B. Okay, so if you look at the transitions on B, B on 0. So look at here, there is no direct transition of B on 0, but look at here, epsilon 0. Epsilon 0 is nothing but 0. So epsilon 0 gets me to C. Okay, so C is going to be a valid transition C. So upon if I'm getting a 0 on B, that means epsilon 0, I can get to C, right? And is there any other way? Is there epsilon? No, there's nothing more. So C is the only state from where to which I can reach from B upon getting a 0. So C is the only state there. What if I'm getting a 1 from B? Okay, so here, look at here, B, look at B. The transition on 1 is defined to itself. So let's fill that first. So B on 1 goes to B itself. So if we have to also look at all the possible epsilon transitions. So if you look at here, B on epsilon 1 goes to C. B on epsilon 1 goes to C. Remember, epsilon 1 is nothing but 1. So B on epsilon 1 goes to C. So C is also possible here. So we can add C also here. Right. Now we also want to look at the transitions from C, from state C. What if I'm giving symbols 0 on to state C, C on 0? So if you look at C on 0, we can see that C on 0 goes to C itself, and there are no epsilon transitions outside of C. So the only thing to consider here is C, just C. Okay, so I can write C alone here. Similarly, for transition 1, you can see that there are no, since there are no epsilon transitions outside of C, then it means that C on 1 also gives me just C. So I can fill in that. Okay. Now that we have got all the transitions, right? We have got all the transitions. We can actually draw the diagram, transition diagram for the same. So let me erase these stuff and draw the transition diagram. Now, before actually moving into the transition diagram, we have to also identify the final states. That's very important, right? So we already know that C was given as a final state in our epsilon NFA. And we also want to check the possibility of any other, any other final states. Also remember that A was a starting state here. So we have to indicate A with an arrow like that. And similarly, we also want to check the possibility of any other final states. So look at here. You can reach to C just by epsilon moves. You can just reach to C just by epsilon moves. Okay, from A, and similarly also from B. Okay, so if in such a case, we can say that A and B are also final states. So it means that all the states from which the final state can be reached via epsilon transitions are also the final states in your NFA. So look at here. So I'm going to define it like this. So if you look at here, all the states from which you can reach to the original final state, which is already defined in your epsilon NFA by just via epsilon transitions. So look at here. From A, you can just use epsilon transition to reach C. So epsilon gets you to C. Similarly, from B, an epsilon transition gets you to C. Okay, so in that case, you can reach to C from A just by using epsilon transitions. Similarly, you can also reach to C from B just by using epsilon transitions. So what we are going to do here is that we are going to mark such states as final states. So A and B both now becomes the final state. So we have to mark both A and B as the final state here. So look at here, A is a starting state and a final state. B and C are final states. Now, so now we are all set to draw the diagram for representing the NFA. So we'll start with A, which is our starting state, and remember A is also a final state. So we have to double circle this, and from A, upon zero transition, we know that it goes to A, B, and C. So it goes to zero transition, goes to A itself. It also goes to B. So, and remember B is also a final state. So the zero transition, oh, let me erase this. Okay, zero transition goes to B also, and C is also a final state here. And from A, upon zero transition, you can also go to C. Okay, so I will indicate like this. Okay, so this is what we have identified now. So we are not very sure about the connection from B to C. Okay, so let's draw one by one. Okay, so what we know now is that A, B, C all are final states. A is a starting state, and upon getting zero from A, you can go to A itself. You can also go to B. You can also go to C. So that's okay. Now from A on one, you can see here A on one by A on one, I can go to B and C. Okay, so so what I can do here is that I can it means that I from while getting if you get a 1 from A, I can actually go to B and C. So I can add one here. Okay, this means that A on 1 gets me to B. Similarly, A on 1 gets me also to C. Right? Okay. Now let's look at the transitions of B. The transitions of B as indicated in this table is that B on 0 gets me to only C. Okay, B on 0 gets me to C. Okay, so let me draw that. B on 0 gets me to C. Similarly, B on 1 gets me to B and C. Okay, so let's draw it. B on 1 gets me to B as well as C. So I can add a 1 also here. It's going to be 0, 1. Okay. Now we have written the transitions from B. Now let's look at the transitions from C. C on 0 just gives me C. Similarly, C on 1 just gives me 1. So C on 1 gives me C. So the transitions of 0 and 1 both are defined to C itself. So this is going to be another transition. So look at this. In this diagram, this is just an NFA. This is a pure NFA without any epsilon transitions. So we are successful in converting the given epsilon NFA to an NFA. So this is the direct commonsensical approach of converting a given epsilon NFA to an NFA. So we will also look at how, there are some mathematical definitions for doing the same thing. Okay, it is a little bit involved, but let's go through it and understand it. Sometimes you may not be able to get a clear understanding of the mathematical formula based approach in the first time. Okay, but you have to revise once or twice to get used to it. And remember, the direct method that I have applied here is the easiest one. If you're not very careless enough to make some mistakes. So the mathematical approach is a little more involved. Okay, a little more involved. We will take a lot of time, but if you do it in a step-by-step way, the answer is guaranteed. So when you're applying the direct trick of converting epsilon NFA to NFA, there are chances that you may run into mistakes. Okay. So even in both cases, you have to be very careful. So let's also look at the mathematical definition of how we can do this, mathematical way of how we can do this using a predefined formula. Now, what we are going to do here is that we are going to take the very same example with which we discussed the conversion. This is an epsilon NFA, the very same epsilon NFA we are taking, and then we are going to solve. We are going to convert it into an NFA using the mathematical approach, right? So what we are interested in is to convert this epsilon NFA to an NFA. So what we essentially need to find are the following transition functions. So that is delta of a comma 0, right? So I'm talking with regard to NFA, right? So in my final NFA, to draw my final NFA, I need all these delta of a comma 0. Similarly, I also need delta of a comma 1. Also, I need delta of b comma 0, delta of b comma 1. Similarly, I also need delta of c comma 0 and delta of c comma 1. So all these are required to, once we know all these, this is going to be a set of some states, this is going to be some set of some states. Okay, so once we know all of this, this is going to be very trivial. Okay, so we can identify that a comma 0, delta of a comma 0 was ABC. Okay, from our previous experience. In the previous way, in the previous slide, when we solved it using the direct method, we could identify that delta of a comma 0 actually goes to every state. That is, it's going to be a set of A, B, and C. Now we want to find it mathematically. So that's what we are interested in. So what we are interested in is to find all these sets. So we need to find all these sets. Okay, so we'll get an answer for a comma 1, b comma 0, b comma 1, similarly c comma 0, c comma 1. So you'll get an answer for all this. Okay, once you get the answer, then it's very trivial to draw its transition diagram. Okay, so if you are able to, there is a method for solving delta of delta of a state using a transition, the transition on A on a particular symbol. Okay, so let's explore it further, and we can just solve for delta of a comma 0, and solving all the other things are going to be the very, we can solve all other transitions in the very same way. Okay, so what I'm going to do here is I'm going to illustrate this using by solving delta of a comma 0. Okay, so let's erase the rest of the things and then get started. Okay, let's get started. Let's first define what is delta of a comma 0. And once you define delta of a comma 0, finding all other transitions will be very similar. Okay, so I'm going to use a blue color in this side. Okay, because things that I'm going to write to the right hand side of this equal to symbol all refers to the epsilon NFA. And remember, this thing delta of a comma 0 is actually referring to the NFA. Okay, so we want to find what will happen if you are getting a 0 on an A in your resulting NFA. So towards the right of this equation, whatever I'm going to write refers to the things from the epsilon NFA, right? So I'm going to write it from here, but this is a very big, this is a little big kind of an formula. Okay, so you have to stay till the end. So what we are actually going to find initially is that we are going to look at the epsilon closure of, okay, epsilon closure of A. So okay, so remember, when you find the epsilon closure of A, you may get different states as answer. For example, you may get A, B, and C. Okay, so you have to, the first thing is that you need to find the epsilon closure of A, and then take a apply transition function on all the states in the epsilon closure of A with 0. So this is what we are going to do now. Okay, so now again, remember that the delta is a transition function applied on the epsilon closure of A upon 0. Okay, so this will again result, this particular formula, this particular formula will again result in some states. Okay, for example, it may result in A comma B, something similar to that. So you're actually defining the the transitions on the epsilon closure of A upon 0. So you'll get some states as the result. So now what we are going to do is that we are going to find the epsilon closure of that. Okay. So what we are going to do here is that we are going to find the epsilon closure of that. So we have to indicate that here. So we are going to find an epsilon closure of this. Okay. So the epsilon closure of this entire thing. Okay. So let me make it very clear. This is going to be the epsilon closure of this. Okay. Now let us find, let us unfold this equation now. So first what we want to do here is that we need to find, I will use a different color so that it becomes more visible. So first I will find epsilon closure of A. So from the diagram itself, we can identify that, epsilon closure of A contains all the states, all the states that you can reach from A just by making use of epsilon moves. So remember, from A we can just utilize an epsilon to reach a B. Again, there is an epsilon which allows you to reach C. So the epsilon closure of A will contain A, B, and C. Okay. So let's write it now. So the epsilon closure of A will contain A, B, and C. So let's represent it as a set. Now, what I'm interested in is to find the transition on all these states upon 0. Okay, so I'm going to find the transition of all these states upon 0. Okay. Now, when you can actually refer to the epsilon-NFA diagram for finding this. Now, look at here. Now, I want to find epsilon, the transition of A on 0, which means that it's going to be that's going to be A itself. Okay, so let me write the transitions here. So let me write the transitions. So transition of A on 0 is A itself. Look at here. Transition of B on 0. B on 0 is not defined, so it's going to be a null set. Okay, so it's going to be a null set here. And what about C? Transition of C. C on 0 goes to C itself. So I have to write C here. Okay. So these are the things, the states that I've received. So you can actually, the null state, you can actually avoid this. So what I'm interested in is to find the epsilon closure of this one. Okay, so let me do it. So I want to finally find the epsilon closure of this quantity. So which means I have to find the epsilon closure of A, I have to find the epsilon closure of the null set, and I have to find the epsilon closure for C. Okay, so we already know that we have already discussed that epsilon closure of null is a null. Okay, what about the epsilon closure of an A? Epsilon closure of an A, we have already identified it as A, B, C, right? So this is going to be A, B, C. What about the epsilon closure of C? So you can see from the diagram that there is no epsilon transitions defined from C. So this is also going to be a null set, right? So this is the situation now. so this is our result: A, B, C, null set, null set. So we can actually cancel off this null set. Those doesn't add any meaning. So the answer that we got is A, B, C. Okay, so what we are essentially getting here now is that we are getting delta of A comma 0 as A, B, C. So let me highlight this with a different color. So we got the answer for we are looking at how to find delta of A comma 0. So we have formulated it in this way, and now we are able to identify that this is the result, A comma B comma C. So this means that in your resulting NFA, A on 0 should have transitions. A on 0 goes to A, B, and as well as to C, right? So now let's now move to let's now do a couple of more transitions, work out a couple of more transitions and make it very clear. Okay, now we got the result for delta of a comma 0 as ABC. So I've written it here. Now we are going to move further. So what we are interested in now here is to find delta of a comma 1. Okay, so let me erase this. So I'm going to find delta of a comma 1. Okay, so I'm going to find delta of a comma 1. So I'm going to replace my formula with 1. Okay, so let's now start. So first thing what we want to find is epsilon closure of A. We know that it is ABC. Okay, so this is going to be ABC, and we want to find the delta, transition of ABC on 1. Okay, so this is what we are interested now. Now, if you look at A, we have to find each one of them. So from the transition, from the epsilon NFA given, we can easily identify this. So if you look at here, from A, there is no transitions defined on 1. Okay, so that becomes that's going to be a null set. Okay, since there are no transitions defined on 1, it's going to be null set. And what about transition of B on 1? Okay, so you can see here that B on 1 goes to B itself. Okay, so you have to write it as B. What about C on 1? You can see here that C on 1 also goes to C. Okay, so just write C there. Okay, now we have got the result of delta of A, B, C on 1. This is going to be null set, comma B, comma C. Now we want to find the epsilon closure of this. So we are interested in finding the epsilon closure of all these. So we know that epsilon closure of a null is a null. Epsilon closure of B. Okay, you look at the figure and identify the epsilon closure of B. It is going to be B and C, right? Similarly, epsilon closure of C. So if you look at C, there are no epsilon transitions from C, so it's going to be a null set. Okay, so the result that we got here is null set B, null set comma B comma C comma null set. So we can just avoid these null values and then take, our answer is B comma C. So we can write the answer on top. So what we got now is delta of A comma 1. We got it as BC. Okay. Okay, the very same way you have to proceed until you get, you also have to find delta of A comma, delta of B comma 0, delta of B comma 1, delta of C comma 0, delta of C comma 1, etc. So I'm leaving it as an assignment for you. Okay, so you have to find all this and then make sure that we are getting the very same result. When we, you can actually refer to the result that we got in the previous slide when we did it directly using the commonsensical approach. Okay, so I think we got for A comma 0 we got ABC, and A comma 1 we got B comma C. Okay, so those two results are the very same results that we got in the direct conversion. So you can also check for delta of B comma 0. Okay, and delta of B comma 1. Similarly, delta of C comma 0 and delta of C comma 1. So you can work out this. So you can actually cross check the results. Delta of B comma 0, we got it as C. And delta of B comma 1, we got it as BC. And delta of C comma 0 was C. Similarly, delta of C comma 1 was also C. Okay, so these are the results that we got. So you can apply the mathematical, formula based approach and then verify that you're getting all these results. Okay, so given a problem, you can solve it using the mathematical approach or the direct method, commonsensical approach. But it depends on how much you want to write. If you want to write more, you obviously have to follow the mathematical approach. It gives it kinds of gives you a guarantee that you will get the results exactly. So if you're doing the direct method, you will just get the results. You don't have to work. You don't have to write more. You're going to get the results very soon. But remember, there can be a chance of error there. So if you apply the mathematical formulation and do things very carefully, you'll get the results 100%.